Hi everyone, Assalamualaikum warahmatullahi wabarakatuh, and a very good morning. So today is where I want to record for the extra lecture class. So because I want to finish chapter 6 by the end of this week. Yes. So today we're going into chapter 6.2, Equilibrium Constants Part 1. So at the end of the lesson, students should be able to, number 1, define homogeneous and heterogeneous equilibria. Number 2, write expressions for equilibrium constants in terms of concentration Kc and partial pressure Kp for homogeneous and heterogeneous systems. And C, use the equation Kp equals to Kc RT to the power of delta n to solve equilibrium problems. So, let's see first, what is homogeneous equilibrium? So, homogeneous equilibrium is the products and reactants which are in the same phase. Where, for example, here we got dinitrogen tetroxide decomposed into 2 mole of nitrogen dioxide. These two reactants and products are all in the gas phase, are in the same phase. And the next example is 2 mole of sulfur dioxide react with oxygen to form 2 mole of sulfur trioxide. So all these are in gas phase. Same goes to this. This one are all in aqueous phase. So when the products and reactants are in the same phase, that is when we call the system is in homogeneous equilibrium. Okay, next, heterogeneous equilibrium. So what is heterogeneous equilibrium? When the products and the reactants are in different phase or not in the same phase. For example, when pentane react with oxygen gas, it forms carbon dioxide and water. So this one of the reactant is in liquid and one of the reactant is in gas. And same goes to this product, gas and liquid. So all of this exists in different phase. So this is when we call this system is in the heterogeneous equilibrium system. So let's see how we are going to write the Kc expressions. So equilibrium constants exist as in terms of concentration and partial pressure. So when in concentration, we wrote it at Kc, and in terms of partial pressure, we wrote it as Kp. So for Kc expression, we have here the general equation is AA plus BB forming CC plus DD. So, to find the equilibrium constant in terms of concentration, we need to equal it to the multiplication of concentration of product divided by the multiplication of concentration of reactant. So, C to the power of C times D to the power of small letter d, because this is actually the stoichiometric coefficient. Okay, so you need to put it up here. Okay. So for example, we have the dinitrogen tetroxide decomposed into 2 mole of nitrogen dioxide. So to write the Kc expression for this reaction, it is Kc is equals to NO2 squared divided by N2O4. Okay, in terms of concentration. Okay, same goes to this one. Okay, so this is for homogeneous equilibrium, where the reacting species are in the same phase. Okay. Okay, how about the Kc expressions for heterogeneous equilibrium? So since there is solid here and gas for here, just bear in your mind that the concentration for pure solid and liquid will be constant throughout the reaction. So hence, we cancel this out to have Kc is equals to concentration of CO2 and Kp because partial pressure is only applicable for gases. So Kp is equals to only partial pressure of carbon dioxide. Okay. So we just took the gas phase, okay, because solid phase it does not applicable for both Kc and Kp. We excluded in Kp because it is not gas. We excluded in Kc because the concentration of solid is constant at constant temperature. So the concentration of pure solid, pure liquids and solvents do not appear in the equilibrium constant expression. So let's look at this one. It says here that partial pressure carbon dioxide does not depend on the amount of calcium carbonate and calcium oxide. Okay, so a pure solid always has the same concentration at a given temperature because it has the same number of moles per liter of the solid. So just as it has the same density at any given temperature. The same reason applies to pure liquid. So that is why we does not include pure solid and liquid in the Kc and in the Kc expressions. So to write a Kp expression, so just now kita dah tengok how to write a Kc expression. So just the same as Kc expression, but for Kp we put it as P. So P C to the power of C times P D to the power of D over PA to the power of A times PB to the power of B. So reactant of products over reactant as well. So take note that P is actually equals to the equilibrium partial pressure of the gas. So for example, here we got dinitrogen tetroxide decomposed into 2 moles of the nitrogen dioxide. So the Kp expression for this reaction is partial pressure of nitrogen dioxide squared divided by partial pressure of dinitrogen tetroxide. Okay. Okay. Same goes to this. Okay. Partial pressure of ammonia divided by partial pressure of nitrogen gas times partial pressure of hydrogen gas. Okay. So note that the equilibrium constant expressions Kc or Kp are also called equilibrium law expression. And usually the unit of pressure used for this one is atm. Okay. So for Kp, since we need to find the partial pressure for each of the reacting species, we need to use the ideal gas equation PV equals to nRT, where we can find the partial pressure P equals to N over VRT. So the equilibrium constant for reaction involving gas can also be expressed based on concentration and pressure. Tapi yang selain daripada gas can only express in terms of concentration because the partial pressure only applicable for gas. Okay. Yang ni, for example 1, for exercise 1, you can do it by yourself, okay, for practice. Okay. So now, let's look at example 2. It says that write equilibrium constant expressions for Kc and Kp for the formation of nickel tetracarbonyl, which is used to separate nickel from other impurities. So here, okay. So we do the Kc first. Allah. Kc. So let's see first. Here we got nickel solid plus 4 carbon monoxide to form nickel tetracarbonyl. So this one is gas, this one is gas, this one is solid. So should we include in Kc and Kp expression? No. So we just Kc is equals to product nickel carbonyl. Ada square tak ayat? Over concentration of CO to the power of 4. So this is how you wrote Kc. So Kp is equals to partial pressure of nickel CO4 divided by partial pressure of CO to the power of 4. So this is how you write the Kc and Kp for this reaction. Okay. Okay. This one pun sama lah. Soalan sama je. So the following equilibrium process has been studied. The nitrogen oxide plus oxygen gas to form nitrogen dioxide. So in one experiment, the concentration of the reacting species at equilibrium are found to be 0.0542 molar and 0.127 molar respectively. And okay. So calculate the equilibrium constant Kc. Ni masukkan je. Substitute all the values that dia dah bagi inside the expression to find for you to get the Kc punya value. So this is the Kc punya value. Okay. So now we are going to look at the relationship between Kp and Kc. So in most cases, Kc is not equal to Kp. Okay. So Kc is like here and Kp is like that. Okay, so the relationship that we can use here is Kp equals to Kc RT to the power of delta N. But how is this come from? Okay, so we are going to look at the derivation of Kp and Kc to get this equation. Kp equals to Kc RT to the power of delta N. And note here, delta N is actually equals to the moles of gaseous products minus moles of gaseous reactant. So C plus D minus A plus B. So this is the product. So this is the reactant. Okay. So first step, we need to write the expression for both Kc and Kp. Okay. Second step, we are going to write the expression for each of the partial pressure in Kp, and we are using the ideal gas equation PV equals to nRT because we assume that the gas all behave as ideal gas. So then we can find the partial pressure for A, B, and C and D using the PV equals to nRT, and then we know that the concentration is equals to moles over volume. So we got this here to form concentration A. This here to form concentration B, and this one for concentration C, and this one for concentration D. So we got here as PA equals to concentration A RT, and the same goes for PB and PC and PD. Okay. Now, what we are going to do the next step is we are going to substitute the partial pressure into the Kp expression. So now, the Kp expression is Pc times Pd over Pa or times Pb. So we are going to substitute this, and this, and this into the Kp expression. So we are going to put it like this. Okay. Concentration of CRT times DRT over ART times BRT. So we will get like this. Because kita akan keluarkan RT and the superscript ni, and then kita akan gabungkan the concentration only. So this is actually expression for Kc. So that is why we got Kp equals to Kc times RTC plus D minus A minus B. Sebab ini adalah C, kalau ikut matematik punya kan, C plus D minus A plus B. So dapatlah ni. So this is product. This is reactant. Okay. So this is moles of gases product. This is moles of gases reactant. So that's why we get this one as the final equation for the relationship between Kc and Kp. Okay. Okay, if we have the delta N equals to 0, then we can say that Kp is equals to Kc because 0.0821 T to the power of 0, this one will equals to 1. So when Kc times 1 equals to Kc, so Kp equals to Kc. Okay. Okay, this one you can do it by yourself. Okay, now we are going to look at equilibrium constants part 2. So in this part 2, we are going to calculate Kc, Kp or the quantities of species present at equilibrium and determine the degree of dissociation. Okay, basically in equilibrium problems chapter 6, there are two types of problems. The first one is when we are given the equilibrium quantities. For example, we are given the values for concentration and partial pressure at equilibrium for us to solve or to find the Kc or Kp, just like what we did in part 1. Okay, however, the second type of problem for this part is when we are only given the initial quantities. For example, we are given the initial concentration and initial partial pressure as well as the Kp and Kc. However, we need to find the concentration and partial pressure at equilibrium. So we are going to use one more method, which is called ice table method. So we are going to solve these problems using ice table. So what is ice table? It is when we express the equilibrium concentration in terms of initial concentration and single unknown, which represent the change in concentration. And then we are going to write the equilibrium constant in terms of equilibrium concentration, knowing the value of equilibrium constant to find the x. Okay, first, we know the initial concentration and we know the Kc and Kp. So, bila kita masukkan the value inside the ice table, we are going to use the value of Kc and Kp to find the unknown x. And after we have find the x, we can calculate the equilibrium concentration of all species. Okay, so let's look at this example. It says that at a certain temperature, a mixture of hydrogen gas and iodine was prepared by placing 0.20 mole of hydrogen gas and 0.20 mole of iodine gas into a 2-liter flask. After a period of time, the equilibrium was established. At equilibrium, the concentration of iodine concentration had dropped to 0.02 molar. What is the value of Kc for this reaction at this temperature? So here, the ice table is actually like this. We do the balanced chemical equation here, and then we put this one ice kat sini. So ICE. Okay, so that's why kita panggil dia ice, okay? So initial, change and equilibrium. So initial, we have the mole and the volume, so we can find the concentration. So 0.2 divided by 2 liter, we got 0.1 molar for H2 and I2. And the HI product here, the initial value is 0. Okay, so it says here change. Okay. Change is when for reactant, the sign is always negative. So since the stoichiometric coefficient is 1, so it's just minus x. And I2 pun minus x. Okay, for product, the sign is always plus. So since the stoichiometric coefficient is 2, so that's why we put plus 2x. Okay, for equilibrium, we know that I plus C is equals to 0.1 plus negative x. So we got 0.1 minus x, 0.1 minus x and plus 2x or 2x only. Okay. So we know that at equilibrium, the concentration of iodine gas is 0.02. So now we can find the x. So x equals to 0.1 minus 0.02. So we got x equals to 0.08. So now can we find the equilibrium concentration for each of these? Yes, we now can find for hydrogen gas 0.1 minus 0.02 equals to 0.1 minus 0.08. We got 0.02. And for HI, we get 2 times 0.08, we got 0.16 molar. So this is how you solve this kind of question. Okay. Okay. So to find the Kc, we just need to substitute the value for the concentration inside here to get 64.0. So that is Kc. Ni pun sama je example ni. Tak ada yang lain. Okay. So let's look at this question. Okay. It says that at 1280 degrees Celsius, the equilibrium constant Kc for the reaction bromine gas to form bromine, is 1.1 times 10 to the power of -3. If the initial concentration for Br2 is 0.063 and Br is 0.012 molar, calculate the concentration of this species at equilibrium. Okay, so now just do the ice table macam biasa. So we got this kind of expression and now we need to focus on equilibrium. Okay. Okay, mana? Okay, this one. Okay, so we know that Kc is equals to Br squared over Br2. So when we substitute the unknown into Kc expression, we got 0.012 plus 2x squared over 0.063 minus x equals to 1.1 times 10 negative 3. Okay, when we solve for x, we do the quadratic equation to get 4x squared plus 0.04x plus 0.00144. Okay. Okay, when we use the quadratic formula, we will get these values. X equals to negative 0.0105 and x equals to negative 0.00174. Usually, we got two values which is one positive and one negative. Where when we got the one of the it is positive and one is negative, we just ignore the negative one because we know that the negative value is not acceptable because concentration and partial pressure is always positive. However, when we meet this kind of question where both of the x value is negative, we need to substitute it to find the acceptable value of x. Okay, for example, okay, we need to determine the chemically meaningful negative x value. How? We substitute it. Okay, for example, if we have x equals to negative 0.01015, when we substitute this into this equilibrium, into this, we get for Br2, we got the concentration is 0.0705, and for Br, we got negative 0.009. And this is not acceptable. No concentration is in negative value. So this is wrong. So, for x equals to negative 0.00178, when we substitute into 0.063 minus x, we got the value of concentration of Br2 is 0.0648. And the concentration for Br is 0.00844. So now, both of the value for this is positive, even though the x is negative. So we can say that this value is the acceptable one. So we accept this x rather than this x. So only this x value makes sense chemically because when we substitute into the equilibrium unknown, we get the positive value for the concentration. Okay. So at equilibrium, bromine is 0.00844 molar and bromine gas is equal to 0.0648 molar. Okay. Okay, what are we going to do when for the equilibrium calculation when Kc is very small? So, the concentration change X can often be neglected. Okay, bila concentration of X sangat-sangat kecil, it is equals to A initial minus X is equals to concentration of equilibrium approximately equal to the concentration of initial. Macam tak ada beza. Okay. So, however, you must check whether the assumption is justified or not. We use the 5% rule. If the X divided by the concentration of initial times 100% is less than 5%, then we can assume it okay. Okay, the assumption is okay lah. Maksudnya kita boleh assume. However, if the X divided by concentration of initial times 100% larger than 5%, then we cannot assume that the KC is very small. That the X is neglected, sorry. So, we need to use the quadratic formula. So, let's see the first example here. So, we got COCl2 gas to form carbon monoxide plus Cl2. So, when we use the ice table, we have this following expression. Okay. So, we assume that when we find the KC, the KC given is really small. So, we assume that when we solve for X, we assume that X is very small. Since KC is very small, so we assume that X is also very small. So, dekat sini, dekat bawah ni, when we see here, when we put inside this, so since we assume that X is very small, so 0.5 minus X is approximately sama juga macam 0.5. So tak ada beza. So that is why we just put here as X squared divide by 0.5. So kita biarkan je. Kita tak masukkan di dalam ni. So, X squared divided by 0.5, we got 8.3 times 10 negative 4 SKC. So, when we solve the X squared ni, we got X equals to 2.0 times 10 negative 2. Okay, so when we checking the assumption, we put X divided by initial, we got equals to 4%, which is less than 5%. So, it is okay for us to assume that X is very small and we ignore the X. So, this is okay. Okay? Tak payah guna quadratic formula. Okay, however, for this one, for this kind of, so we can just solve like usual, like biasa-biasa punya, and then got the equation at equilibrium for all the reactant species. Okay, however, for this example, okay, we got this value juga. Okay, when we are going to solve for the X, when we see that the KC is very small, and we are going to assume that since KC is very small, we also assume that X is very small. So, there is no difference here, so we ignore this. Okay, so we use KC is equals to X squared over 0.01 equals to 8.3 times 10 negative 4. However, so, we got X equals to 2.9 times 10 negative 3. However, when we checking the assumption X over initial times 100%, we got 29%, which is very high than 5%. So, we are not going to assume. So, we're going to use the quadratic formula. How? We are going to include this X into the KC expression. So, we are going to solve the X using the quadratic formula. So, X squared plus 8.3 times 10 negative 4X minus 8.3 times 10 negative 6 equals to, buat sendiri lah kan. So, we got two values of X, satu positive, satu negative. But we will ignore the negative because concentration and partial pressure is always positive. So, we just take the positive value. So, X equals to 2.5 times 10 negative 3. So, now we can substitute the value into the ice table. So, kita akan dapat values of the concentration at equilibrium for all the reacting species. So, now we got the new concentration for COCl2 is 7.5 times 10 negative 3 molar. It's completely different from the one yang kita assume tadi. Yang kita assume tadi 2.9 kan times 10 negative 3. Now yang betul-betul lepas kita buat quadratic formula, we get 7.5 times 10 negative 3. Okay. So now we are going to look at the degree of dissociation. So what is dissociation reaction? So dissociation reaction is when the molecule is broken down into smaller molecules, atoms or ion. Okay, example, fraction or the percentage of molecules. So biasanya kita akan guna degree of dissociation equals to the concentration changes or concentration dissociated divide by concentration initial times 100% to get the percentage degree of dissociation, or if we don't times 100%, we just got the fraction of degree of dissociation. So the degree of dissociation can be varies from 0 to 1, where 1 is the complete dissociation, or from 0 to 100%, where 100% is the complete dissociation. Okay. So thermal dissociation is a reversible reaction brought about by the application of heat. So when cool, the products bond again to give the original compound. Ini yang maksud dissociation lah. Sebab dissociation kan the process of breaking down of the molecule into smaller parts of molecule, ion and atoms. Okay, so this is how you find the degree of dissociation. So it says here that the degree of dissociation of dinitrogen tetroxide at 250 degrees Celsius and 1 atm is 0.15. Calculate the degree of dissociation at 250 degrees Celsius and 5 atm. So, what we need to do is, we need to find the partial pressure of each of the species. So, according to Dalton's law of partial pressure, we can see that we can find the, what we call it, partial pressure using this formula, so that we can find the partial pressure of nitrogen dioxide and partial pressure of dinitrogen tetroxide. So we can substitute here into a Kp. Kp is equals to partial pressure nitrogen dioxide squared over partial pressure dinitrogen tetroxide, and we got Kp is equals to 9.21 times 10 to the power of negative 2. Itu untuk 1 atm. But now we need to find it at 5 atm. So for at 5 atm, we are going to do the ice table here. Okay, so the ice table here, we put initial mole. Soalnya apa? Peningnya dia punya ni. Ini bukan initial. It's not initial. It's pressure atm patutnya. Okay. Total number of moles after dissociation. Okay, faham. Okay, class. So, we assume that the initial mole is 1 for the reactant and 0 for the product. Since it says that the degree of dissociation at 1 atm is 0.15. So, maksudnya, here, this changes here is minus 0.15 and the product gains plus 0.15. So, here we will get 1 minus 0.15, so the mole here is 0.85 and 2 times 0.15, so kat sini 0.3. So we got the total number of moles after dissociation is 1.15 mole. Okay, so now let the degree of dissociation at 5 atm equals to X. So same goes juga. So initial mole dia 1 and then for product 0. And we got changes dia kita tahu lagi kan. So minus X and positive X. So we got 1 minus X and 2X. So now the difference is for the partial pressure now we got 2X divided by 1 minus X plus 2X. This one kita guna as apa ni? Kita masukkan the unknown tadi. Okay. So now we get when we substitute the partial pressure into the Kp just now, because Kp is equals to 9.21 times 10 to the power of negative 2, right? So when we substitute into the Kp, we will get X equals to 0.068. So now we can find the degree of dissociation. 0.068 divided by initial divided by 1 times 100%. So we got 6.8%. So on this 6.8% of dinitrogen tetroxide dissociate at 250 and 580 m. Tadi 15 kan, yang ni 6.8 saja. Okay. Okay. Now we are going to look at the part 3, which is we are going to predict the direction of the net reaction by comparing the values of reaction quotient Q and equilibrium constant K. So what is reaction quotient? So reaction quotient is calculated by substituting the initial concentration or the pressure of the reactants and product into Kc and Kp. So kalau Kc and Kp, we use the concentration and pressure at equilibrium. For reaction quotient, we usually use the initial concentration or pressure. So for now, for example, we have Kc like this. For Qc, dia punya Kc and Qc expression sama je. Okay? Cuma bezanya Kc at equilibrium, Qc at any or biasanya at initial concentration. Okay. So now when we for comparing the Q and K. Okay, so how do you know if the reaction has reached equilibrium? And if it hasn't, how do you know in which direction it is progressing to reach equilibrium? So we use the values of Q and K to know whether the reaction has reached equilibrium and to know at which direction the reaction will proceed. Okay, so for example, we have this one. Okay, so there are 3 possible cases. Okay, so now we look at the first case. So the first case is when the Q is less than K. So when Q is less than K, the denominator reactant is large relative to numerator product. So, to reach equilibrium Q equals to K, the product must increase and the reactant must decrease. So, if Q is less than K, reactants will form more product. So, here, the reaction will proceed to the right. Okay, so now the reaction will proceed to the right to form more product until the equilibrium is achieved. So the forward reaction is favored in this case. Okay, when Q is larger than K, so it means that the denominator reactant is small relative to numerator product. So, to reach equilibrium, Q equals to K, the product must decrease so that the reactant can increase. So, if Q is larger than K, the reaction will shift to the left. It will form more products until the equilibrium is achieved. So, the reaction will progress to the left to form more reactant until equilibrium is achieved. So, for Q larger than K, the reverse reaction is favored. Okay, and for the last possible cases, Q equals to K is when the reactant and product has attained their equilibrium values. Okay, so if Q equals to K, the production of reactant and product are at the same rate. So, no further net change. Sebab dia orang dah memang dekat equilibrium. Okay. So, here is the in picture punya form lah. Okay, so kalau Q lagi kecil daripada K, when Q is smaller than K, hence the product is favoured. However, when Q is larger than K, the reactant is favoured. Okay, so the reactant will shift its reaction to either left or right until the equilibrium is achieved. Okay. Okay. Alright. So, yeah. So, kat sini kan dia kata, so this is before equilibrium, this is after equilibrium. Before equilibrium, the Q is larger than K. Okay, so before equilibrium is reached, the concentration are changing continuously. Okay, so once the equilibrium is reached, and any time thereafter, Q equals to K. Maksudnya dah sama. So, dua-dua Q equals to K. Okay, this one. Okay, look at this example 6 here. So it says that Kc for the formation of nitrosyl chloride and orange-yellow compound from nitric oxide and molecular chlorine is 6.5 times 10 to the power of 4 at 35 degrees Celsius. In certain experiment, 2.0 times 10 negative 2 mole of nitric oxide, 8.3 times 10 negative 3 mole of Cl2 and 6.8 moles of nitrosyl chloride are mixed in a 2.0 liter flask. In which direction will the system proceed? So, dia bagi kita mole, kita boleh cari concentration. So, after we find the concentration, this is the initial, right? This is the initial concentration. So, what we need is, we need to find the QC because QC is, sebab dia dah bagi kita KC. KC is at equilibrium. But dia bagi kita moles in terms of initial concentration, in terms of initial mole. So we have to find the initial concentration and find the QC. And then we can compare the QC with KC. Okay, so when we find the QC, okay, first we need to find the moles first, the concentration first. So then we substitute the concentration into the QC. Then we will get QC is equals to 2.75 times to the power of 7. Okay, which is QC is larger than KC. So when QC is larger than KC, the reaction is not at equilibrium. And the reaction will proceed to the left. Maksudnya dia lagi prefer forming more reactant until QC equals to KC or until the equilibrium is achieved. Okay, so this is how you solve this kind of question. Okay, same goes to the, okay. So now we have we have finished chapter 6.2. So in the Wednesday's lecture, we are going to finish chapter 6.3, and this Friday you are going to have your UPS 3. So I wish you all the best lah. Okay, so please watch this video and focus on your tutorial class so that you can understand more about this chapter, because nanti masa tutorial lagi faham lah sebab you buat tutorial kan. So this one I will stop here for now. So yeah, thank you for watching and have a good day. Bye bye. Assalamualaikum.